Hi everyone, it's Mrs. Gifford here, and today we're going to talk about section 9.5, all about symmetry. So after today's lesson, you'll be able to identify line and rotational symmetries in both two-dimensional and three-dimensional figures. So let's take a look at a bunch of vocabulary. The first one has to do with symmetry, and we look at reflections, rotations, translations, and glides that map a figure onto itself. So the first one, or the next term here, is line symmetry. Okay, and it's line symmetry if we can reflect it across that line. And we call that specifically a line of symmetry. So imagine that you rotate this figure across that line of symmetry. Excuse me. So the next term is rotational symmetry. And with rotational symmetry, instead of drawing a line, like line symmetry, and rotational symmetry, we look to see at what angle can we rotate a figure so that it maps it on top of itself. And so we look at what point that we can rotate that figure, and we call that point the center of symmetry. So down here with the square, there's a bunch of different examples that we can do to rotate it so it ends up landing right back on itself. The next vocabulary term is order of symmetry, and that's the number of times a figure can map itself onto itself between 0 and 360 degrees. And we have something called the magnitude of symmetry, also known as the angle of rotation. And it's the smallest angle a figure can be rotated so it maps onto itself. And to find the magnitude of symmetry, we're going to take 360 degrees. And we're going to divide it by the order. So once we can figure out how many times it rotates onto itself, to find that magnitude or the angle of rotation, you take 360 divided by the order. And then the last two vocabulary terms are plane symmetry. Plane symmetry has to do with the fact that if you can, it's almost like a line of reflection, but if you can cut a figure in half and then rotate it across that plane, okay, then we call that plane symmetry. So here's our three-dimensional figure. And then an axis of symmetry, if you can imagine that you drill a hole through the top of the figure and goes all the way through, maybe like stick a dowel through it, and then you can rotate it around, that's considered axis of symmetry. So those are your vocabulary terms. Let's take a look at a few examples. So example number 1, state whether the figure has line symmetry, and if you say yes, copy the figure and draw all the lines of symmetry, and then state their number, meaning how many does it have. So here's our first one. We have a parallelogram, and if you try to take a line and try to cut that parallelogram in any way, we should hopefully recognize that this one does not have any line of symmetry, because we can't reflect it across that line and get it to map on top of itself. So with a parallelogram, this does not have any line symmetry. Again, we have to be able to flip it or reflect it across any of those lines that we're thinking of in order for it to have that line symmetry. The second one is this triangle, equilateral triangle. So I'm going to do the same thing. I'm going to grab a line here, pick a different color, and I know that I can draw a line from its vertex straight through. Try to move it over a little bit so it matches. So there's one of them, and if I do it again, I can do that from each of the other two vertices. Imagine that I flip that figure across each of those lines. That original triangle is going to match up. Okay, I can reflect it. So we say yes, this triangle does have line symmetry, and because we said yes, we say that it has 3 lines of symmetry, because there are 3 lines that we can draw to get it to reflect across those lines. All right, example 2. Similarly to the one before, but we're going to talk about rotational symmetry. So we're going to look at this flower. If we say yes, that this has rotational symmetry, there's 2 things that we need to do. Well, we're going to copy the flower, we're going to locate the center, and we're going to state the order and magnitude of symmetry. So what do you think as you look at this flower? Do you think this has rotational symmetry? Yes, it does. It does have rotational symmetry. So the first thing that we want to do is indicate where that center is. Okay, and there is our center of symmetry. Then the next thing that we want to do is state the order of that symmetry. And again, in this case, the order has to do with where we can rotate that through. And actually, I'm going to draw a line through here and here. Because it has these 5 petals that are all similar, we can say that this has, we'll find the magnitude in a second, we can say that this has an order of 5. Okay, and again, we talked about the fact that in order to find the magnitude of symmetry, we have to take 360 degrees and divide it by 5. And what do we get? We get 72 degrees. So what that's saying is if we were to take this flower and rotate it 72 degrees in any direction, in either clockwise or counterclockwise, that flower would match itself up. So there's the 72 degrees angle of symmetry, or angle of rotation, excuse me. Okay, last example has to do with plane symmetry and axis symmetry. So we're going to state whether each of these, there's 2 examples for this, if they appear to have either plane symmetry, axis symmetry, or both or neither. Again, just a reminder, plane symmetry is where you can kind of cut it in half like a box, a shoe box. If you can cut it in half and then flip it around that plane, does it match up? In this case, a ball glove does not, nor does it have an axis of symmetry. So in this case, oops, I've still got the arrow going on. In this case, we say neither, because we can't cut the glove in half to get it to rotate it around, nor can we rotate it through any point of the glove, like if we were to drill a hole through the middle of it. Okay, the second one is the bat, this wooden bat, and 2 questions. 1, does it have plane symmetry? And 2, does it have axis symmetry? And so the first thing that I can recognize when I look at this is if I take a saw, I can cut that bat completely in half. We didn't do a very good job of lining it up, but I can take a saw and cut it completely in half. And both sides of the bat would match up. Okay, and so there's our plane symmetry. And not only that, but imagine if we were to stand that bat up on end and drill a hole down through the grip, all the way through the bottom of the bat, we could rotate that bat around and it would still look like the exact same bat. So we say that it has both plane and axis symmetry because, again, we can cut that bat in half and then we can also drill a hole through the middle of it and rotate it around. So there you have it, folks. Pretty straightforward with line and rotational symmetry.